Hello everybody, this is Mr. Strager, and welcome back to another Big Ideas lesson. Today we're starting off Unit 6 in Section 6.1. Unit 6 is all about exponents and radicals. Now these are two words that we might have heard a long time ago in middle school, but probably haven't seen much of since then. Before we jump into what these things are, I have a quick little question for you. This question doesn't really have too much to do with exponents themselves, but you'll see why we're asking it in a second. Let's say I have 50 nickels in my pocket. And in order to count them up, I am taking one out of my pocket at a time, putting it on the table. So I take a nickel out, that's 5 cents. I take another one out, it's another 5 cents. I take another one, that's another 5 cents. And I keep on taking out one nickel at a time until I add up all 50 nickels. Now, you could figure out how much change you have based on just adding up 5 plus 5 plus 5 plus 5 plus 5 50 times. But it seems a little bit excessive, right? Repeated addition is not the best way to count when you have a large number of things. Instead of counting 5 plus 5 plus 5 plus 5 plus 5 over and over again, how can I change this into a simpler problem for us? Well, 5 50 times, we can just do 5 times 50. The amount of nickels I have times 5 cents. Well, that'll give us $2.50. And it's much quicker than counting up 50 nickels, right? Multiplication is just repeated addition, and it's a shorter way of doing it. It makes things a lot simpler. But what happens if we have repeated multiplication? Let's say, for instance, that we have 2 times 2 times 2 times 2 times 2 times 2 times 2. It's a lot of 2's to be multiplying through. I mean, yes, you can do it, but it'll probably take you a couple of minutes. Instead of doing repeated multiplication, which could theoretically go on forever, let's instead try to think of a way of doing this that doesn't involve multiplying over and over again. Well, there is a notation for repeated multiplication as well. Instead of having something like this, where it's repeated addition turns into multiplication, repeated multiplication can be rewritten in this format. We say, we're trying to multiply the number 2 7 times, right? So we put a little 7 up above it to indicate the number 2 should be multiplied with itself 7 times. This is the basis of exponents. All we're talking about this unit, with exponents and everything, are different ways of doing repeated multiplication in a shorter way. If we go back to our notes, we're going to focus on this in a second, but for now, I want us to take a look at the left side of our notes. I want you to draw a dividing line right down the middle, and we're going to talk about what an exponent is before we go into detail about how to use them. So, first things first. With an exponent, or with a power we should say, there's a couple pieces. Let's take that exponent that we just talked about, 2 to the 7th. Like so. This entire structure is what we call a power. This entire thing is a power. And we read it off like this, 2 to the 7th power. You might even hear me say 2 to the 7th. 2 to the 7th power just means 2 multiplied by itself 7 times. In this structure, there are two pieces. The base is the big number that is on the bottom, and that's what's being multiplied over and over and over again. Up top, we have the exponent. And the exponent just tells us how many times that number is being multiplied. So let me ask you a quick question here. Let's say I gave you the power 15 to the 22nd. How do we represent this in multiplication? Would it be 15 times 15 times 15 over and over again, 22 times? Or would it be 22 times 22 times 22 times 22, 15 times? Well, the correct answer would be this one up here. 15 to the 22nd power just means 15, because that's the base, times itself 22 times. It's the same with our examples before. 2 to the 7th could just be written out as 7 different 2's being multiplied together. Like this. So let's take a look at this other side of the page. I want you to set up your page exactly like this as well. We're going to make a small little table here. Up at the top, we have 2 to the 4th power, 3rd, 2nd, 1st, and we're sort of going down from there. Pause this video and write out this table for yourself. Hopefully, you took a chance to pause the video and try it out. Here's the deal with this table. I want us to start discussing exponents and seeing patterns within exponents. The best way to talk about them is through patterns. Let's start off by taking a look and seeing if we can translate some of these exponents into multiplication. So just like how we wrote out 2 to the 7th power as 7 2's being multiplied together, we could write, for instance, 2 to the 2nd power as 2 2's being multiplied together, right? Well, we know that 2 times 2 equals 4. What about 2 to the 3rd power? How can we write that one out? Well, 2 is the base, so we're going to have a bunch of 2's being multiplied. And number 3 tells us it should be 3 2's being multiplied together. 2 times 2 times 2. What about 2 to the 4th? Well, we should be able to guess that it's 4 2's being multiplied together. What about 2 to the 1st power? What will we write down here? Well, this notation is just telling us that there is 1, 2. So it's just the number 2. As we go through and start solving some of these, 2 just equals 2. 2 times 2, we said, is 4. 2 times 2 times 2, well, hang on a second. We know that 2 times 2 is 4. We talked about that last time. So what happens when we multiply that by 2? Well, 4 times 2 is 8. And 2 to the 4th, we can take a look and see 2 times 2 times 2 is already 8. So what happens when we multiply that by another 2? Well, we get 16. What we're seeing here is as we go up these numbers, there is a pattern in place. To go from 2 to the 1st to 2 to the 2nd, we multiply by 2. 2 times 2 is 4. To get to the next one, 4 times 2 gives us 8. 8 times 2 gives us 16. So going up this chain, all we're doing when we add another number to our exponent is we're multiplying by 2. This pattern is nice, but it doesn't tell us too much about it, right? It doesn't tell us too much about exponents. Sure, it tells us how to get to 2 to the 5th. We just multiply 16 by 2. And 2 to the 6th, we'll be multiplying 2 to the 5th times 2. And you just keep multiplying by 2 to go up, but it's not going to help us going down, right? Or is it? Let's take a look and see what pattern we notice as we go from one number down to the one below it. So from 16 to 8, how do we get there? And 8 to 4, how do we get there? Is there a pattern going down that we could keep following with the rest of our table here? There is. Going down the chart, the way we get to 8 from 16 is we divide by 2. 16 divided by 2 is 8. 8 divided by 2 is 4. And 4 divided by 2 is 2. So just like we multiply by 2 when the exponents go up, we divide by 2 when the exponents go down. Pretty interesting, huh? Now that being said, I do want to bring up, the only reason we're multiplying by 2 and dividing by 2 is because 2 is our base. That's the number that we're multiplying over and over again. If our number was, say, 3 instead, our pattern might be different. For instance, how do we get from 3 to 9? Well, we multiply by 3. 3 times 3 is 9. And 9 times 3 is 27. And 27 times 3 is 81. And the same goes backwards, where it's dividing by 3. So the pattern is, going up, we multiply, going down, we divide. So can we continue this pattern going down? Let's take a look at 2 to the 0. This is a little bit of a weird notation because this is basically saying, hey, multiply 2 0 times. You can't multiply something 0 times. But would that mean that the answer is 0? Would it mean the answer is 1? Would it mean it's no solutions? Would it mean it's 2? Well, by following our pattern, we can find the next answer. Going down, our pattern is to divide by 2. So what's 2 divided by 2? 2 divided by 2 is 1. 2 to the 0 power is 1. A little weird, right? It turns out that this is a rule across all exponents. And down below, we call this the zero exponent rule. Here's the rule. It basically goes like this. For any number, except for 0, which we're not going to really talk too much about, that number to the 0 power is just 1. Think about it. If we go down this chart we did with number 3, and we try to find 3 to the 0, well, we keep dividing by 3 every time. 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. And 3 divided by 3 is, well, also 1. Any number to the 0 power is 1. So, for instance, 117 to the 0 power. It's pretty easy to calculate. Since it's to the 0 power, we just say that it equals 1. This also works algebraically, though. Let's say I had the following expression. X to the 0 times y to the 0 times 6. This looks complicated, but then you realize x to the 0 is just 1. Y to the 0 is also just 1. So this is really 1 times 6. And 1 times anything is itself, so 1 times 1 times 6 is just 6. Zero exponents are very useful because they're very easy to simplify. But we didn't just stop our chart at 0. We still have a little bit to go here. When we talk about negative exponents, it's not very intuitive. It doesn't come very naturally to us. I mean, you can't count something a negative amount of times. But, nonetheless, negative exponents do exist. And by following our pattern, we can find what they look like. So let's keep going down. What's 1 divided by 2? Well, it won't give you a whole number anymore. 1 divided by 2, we can write as 1 over 2. And when we simplify that, that's just 1/2. It's already simplified. Interesting. So when we get negative exponents, we start turning into fractions. Getting bigger exponents makes us go bigger. Smaller exponents and negative exponents make us go smaller. Let's try this again with the next one. Now, many people might not remember how to divide a fraction by 2. Here's a little trick to keep in mind. Let's say we have the fraction 2/3. I want to multiply 2/3 by 5. When we multiply a fraction by a whole number, you're really just multiplying that whole number with the numerator. the denominator is going to stick around. 2/3 times 5 is the same as 2 times 5 over 3, or 10/3. See how we just multiplied 2 and 5? When you divide, it's kind of the opposite. Dividing by a whole number means that you are going to be multiplying this with the denominator. You might remember it as keep, change, flip, where instead of dividing by 5, you keep this, you change the division into a multiplication symbol, and you flip the 5 to be 1 over 5. Well, that's just the same thing. It's just having us multiply 2 times 1 and 3 times 5. Either way, your answer still ends up being 2 over 15. So let's apply this with dividing 1/2 by 2. Well, 1/2 divided by 2, that means that we're multiplying the denominator by 2. 1 over 2 times 2. Well, what's 1 over 2 times 2? It's 1/4. So go from 1/2 to 1/4. Let's divide by 2 one last time. Although we know this pattern could continue on forever. Well, we're just multiplying the denominator by 2 again, right? So it's almost like we have 1 over 2 times 2 times 2. Or 1 over 4 times 2. What's 4 times 2? Well, that's 8. But hang on a second. That sounds familiar. It sounds like we were talking about these numbers a little bit before. In fact, 2 to the negative third is 1 over 8. Where else do we see an 8 in our table? All the way up here with 2 to the third, right? 2 to the third is 8, and 2 to the negative third is 1 over 8. Is that a coincidence? Well, let's check another one. Let's check 2 to the negative second power. Well, that's 1 over 4, and 2 to the regular second power is just 4. So what's the big idea here? Each time you divide by 2, you're multiplying another 2 in the denominator, right? Here, when we divided by 2 a third time, there were 3 2's in the denominator. Whereas with 2 to the third, we multiplied 3 2's in the numerator. It looks like 2 to the negative third is just 2 to the third on the bottom of a fraction. This is the relationship we have with negative exponents. We don't like to have negative exponents. They're not intuitive to our brains. But we can turn them into normal positive exponents. Here's the rule. Let's say we have 4 to the negative second power in our numerator. Remember that if we wanted to, we could put this as a fraction over 1. We don't like 4 to the negative second power. But what we've learned is, for instance, 2 to the negative second power is just 1 over 2 to the second power. So 4 to the negative second power is just 1 over 4 to the second power. And what's 4 squared? What's 4 times 4? It's 16. 4 to the negative second is just 1 over 16. So the rule seems to be, at least, that you just put it on the bottom of a fraction. But I want to give you a little bit of a weird one that's going to test that. What if I gave you 1 over 4 to the negative third power? Uh-oh. Now, our negative exponent is on the bottom of a fraction. It's in the denominator. Well, if it's already in the denominator, what can we do? We can't put it in the denominator again. Here's the secret. In order to get rid of a negative exponent, you just need to flip it over your fraction bar. So in this case, our negative exponent is on the bottom. So to turn it positive, we just have to flip it to be on top. When we do, this becomes 4 cubed over, well, since there's nothing on bottom anymore, we put a 1. But we know anything over 1 is just the numerator, 4 cubed. It's a little bit weird, but think about the fact that any number can be a fraction over 1. All we're doing is we're flipping that number over the fraction bar if it has a negative exponent. So, for instance, if I gave you 2 to the 4th power, 2 to the negative 4th power, on the top of a fraction bar, in other words, 2 to the negative 4th over 1, in order to get rid of the negative exponent, we have to move this to the bottom. By moving it to the bottom, we get rid of the negative exponent. So this becomes 2 to the 4th on bottom. And what's left on top? Well, there's nothing left on top. So when there's nothing left on top of our fraction, or on the bottom of our fraction, we put a 1. The answer is 1 over 2 to the 4th. Since 2 to the 4th is 16, we know that our final answer here is 1 over 16. But again, if your negative exponent is in the denominator, it's the same thing. We just flip it to the top instead. This one is a little bit harder to memorize, so let's do a couple of quick practice problems. I want you to flip over to the next page. And here's what I would like us to try out. For these exercises up here, we're just asked to evaluate the expression. In other words, what we're really trying to do is, we're just trying to turn it into a number. A single number should be our answer. I want us to try out problems 2, problem 3, problem 7, and if you're looking for a challenge, problem number 6. Pause the video, try out these problems here, and check your answers in just a moment. So go on, pause the video, and we will see. What do we think, y'all? Did you get it? For number 2, it's to the 0 power, so it's just 1. For number 3, because it's a negative exponent, we want to flip it to be on the other side of a fraction bar. Well, since there's no fraction bar, we can imagine it as being 3 to the negative 4 over 1. So when we flip it, it becomes 1 over 3 to the 4th, which is 1 over 81. For number 7, this one was an interesting problem because there were a couple steps to it. Negative 7 to the 0 power, well, it's to the 0 power, so it's just 1. But be careful. The negative sign here isn't being taken to the 0 power. So this becomes to the negative 1st power. When we flip this 4 to the negative 1 over it, it should become 1 over negative 4 to the 1 because the negative sign will stick around. We'll talk about why this is in just a moment. Number 6 was another tough one. The key is, since negative 3 to the negative 2nd power needs to be flipped, we put it on the bottom of the fraction. Since 2 to the negative 3rd needs to be flipped, we put it on top. So we might as well just flip-flop the fraction. 2 to the 3rd over negative 3 to the 2nd. Well, 3 squared is 9, so negative 3 squared is negative 9. 2 to the 3rd is 8. This brings up an interesting little dilemma here. And it's the dilemma of, what do we do with negative numbers? And the answer is, it depends. Let's say I have the following 2 problems. Well, let's experiment with what these mean. Let's write negative 3 squared in multiplication. Well, this is saying that negative 3 is being multiplied by itself 2 times. So this is negative 3 times negative 3, right? Well, negative times a negative is a positive. So this becomes positive 9. What about over here? What do we do with this? What's being squared here? Well, this time the negative isn't being squared, it's the 3. So what this is saying is it's saying 3 is being multiplied by itself. And by the way, there's a negative sign hanging out. This, in other words, becomes negative 3 times 3. Well, 3 times 3 is 9, so this is negative 9. There is a big difference between these two. You have to be careful and ask yourself, is our negative sign also being taken to that exponent? If it isn't, don't mess with it. If it is, you have to take it to that power. All right, y'all, we are almost done with the notes at this point. There's a couple other things I want us to touch up on. On page 171, we're going to talk about 2 properties today. The first of these properties is called the product of powers property. You don't really need to remember the names, but it's important that we remember what they mean. Here's the basis of the product of powers property. Let's say I had the following multiplication problem. I had 2 to the 4th times 2 squared. And I want to figure out what this is. Well, I could figure out what 2 to the 4th is, and I could multiply it by whatever 2 squared is, but those numbers might be pretty big. Instead, there's actually a way to simplify this. Let's look at it in terms of multiplication. 2 to the 4th can be written out as 2 times 2 times 2 times 2, right? Well, how can 2 squared be written out? 2 squared is just 2 times 2. Well, this is really then 2 times 2 times 2 times 2 times 2 times 2. In other words, this just becomes a string of 6 2's being multiplied together. Well, we can write 6 2's being multiplied together in a different way. We write it as 2 to the 6th power. In other words, if we just look at the top and bottom of our problem, how do we get from 2 to the 4th times 2 squared to 2 to the 6th? We add the exponents. It's weird, but because we have 4 2's over here and 2 2's over here, by putting all of the 2's together, in other words, adding the number of them, we get 2 to the 6th. So for any exponents that have the same base, it's only worse because we're talking about 6 different 2's here. If this was a 6 or a 7, it wouldn't work. If they have the same base, you can add their exponents. Take a look at the example over here. We have 4 to the 6th times 4 to the 3rd. So what that's really saying is, here are 6 4's, and here are 3 4's. Put them together, how many 4's are you multiplying together? 9 of them, 4 to the 9th. This is really, really crucial, because it helps us combine terms. It simplifies these exponent problems a lot. There is one other way we can simplify here, and it is the quotient of powers property. Now, when we hear the word quotient, we think division. The quotient of powers property says this. Let's say we have 2 to the 7th power divided by 2 to the 4th power. I'm going to use a separate sheet of paper for this because this one's going to get a little bit bigger. But here's the basic idea. 2 to the 7th power is just 7 2's being multiplied together, right? 4, 5, 6, 7. And 2 to the 4th power is just 4 2's being multiplied together. So this is times 1, 2, 3, 4 2's. When you have things in a fraction, or when you are dividing, you can cancel out like terms because multiplication and division are inverses, right? So in other words, if we're multiplying by 2 up here, but then we divide by 2, we can cancel those out. So we can cancel out these 2's right here. But we also have multiplying by 2 and dividing by 2 again. So we can cancel out these 2's. And again, so we can cancel out these 2's. And again, so we can cancel out these 2's. What we end up with is 2 times 2 times 2 in the numerator, and since there's nothing left in the denominator, it's over 1. This is just the same as 2 cubed. 2 to the 7th divided by 2 to the 4th is 2 cubed. What did we do with the exponents to get here, though? Well, we subtracted them, because 7 minus 4 gives us 3. At this point in time, I want you to take a look at a couple more practice problems before we end off the notes for today. We'll talk about part 2, where we'll finish up these notes in a later video. But I do want us to flip back to page 172. Here's some practice to leave off with. You can come to me in class to show me your answers, and I'll be able to show you what the correct answers are. But the problems that I think will help us out the most when practicing out this content are as follows. Problem number 11, because remember, negative exponents can also work with variables. In fact, all of our exponent rules can work with variables. After that, I want you to try out problem number 15. After that, I'd like you to try out problem 16 and 17. And if you're really up for a challenge, problem number 20. Try these problems out and talk to me about it in class because I'd like to see how we do. With that being said, that is day 1 of 6.2 completely finished. Thank you so much, everybody, and have a fantastic rest of your day.